Hello and welcome back to our First Flight kickoff streams. My name is Jess and today we have another exciting project for you to dive into and use to help improve your security auditing skills. These contests are designed as an opportunity for you to apply what you have learned over on Updraft to prepare yourself for a real competitive audit. We have some really exciting contests hitting Codehawk soon, so now is the time to prepare yourselves and improve your skills and your chances of earning some of those huge prize pools. We actually have a huge number of contests coming very, very soon, so make sure to stay tuned for that. As always, if you have any questions about this repo, make sure to pop them in the live chat and we will discuss them at the end of today's stream. Now, let's get started. This week's First Flight is an interesting one. Most of you may have seen that we have launched our Viper courses in the last few weeks, and the repo we're sharing today is part of the Cypher and Updraft Viper course, where we teach you to build a stablecoin smart contract using Moccasin, our custom framework for Viper smart contract development. This is super exciting because Moccasin makes it easy to create and deploy Viper-based smart contracts. To break this down into simple terms, Viper is an alternative to Solidity and Moccasin is Viper's foundry. So Viper, for those of you that don't know, is a Python-like language for Ethereum. It's already used for major DeFi projects like Curve Finance. They have a TVL of over $2.2 billion at the time of filming. So it's already a language that's very much used within the space, but we're trying to drive more adoption here. If we take a look at Python in the Web 2 space, it's used widely for financial systems. So Moccasin and Viper are a great tool to onboard people from Web 2 into Web 3. So now we're looking at this, and it may feel a little bit daunting because a lot of you are coming from from Updraft, where you've learned all of this Solidity and you're ready to put it to the test, and you're thinking, "Oh my gosh, we've got another language to uncover." But it's not as daunting as it looks, especially if you've used Python before. But to be honest, even if you only know Solidity, you can pick up different languages very quickly once you've learned one. The thing is, the language of the contract doesn't really matter. The understanding of the vulnerabilities is what matters. If you have a reentrancy attack in Solidity because you are making a transaction before changing the state of the contract, you're going to see that same attack in a Viper contract. The structure of the code is what we're looking at when we're identifying most vulnerabilities rather than the language that it's written into. So hopefully that makes sense and calms your nerves about moving into a different language and helps prepare you to get stuck into this Viper contest, because it will be very interesting. And learning Viper and taking part in this First Flight will just better your skills and your ability to be more adaptable and learn different languages. I wouldn't veer away from it. It's just that the actual text is written in a different way, but the vulnerabilities are still the same. It depends on the structure. So this week's project is the perfect way to step out of your comfort zone, practice spotting those universal vulnerabilities, and improve your ability to adapt to those different languages. If you do want a more guided approach to Viper and Moccasin, then check out our Updraft courses. But for now, let's take a look at this First Flight and what we've got in store for this week. So for those of you who don't know, First Flights are a brilliant way to practice your skills. We launch these every other week. So this one launched yesterday. The contest will be open until next Thursday. So you've got time to go through those Updraft courses, dig a little deeper into Viper, and then head over to this First Flight to get stuck in. But let's take a look at what this contest is. So this project is meant to be a stablecoin where users deposit WETH and WBTC in exchange for a token that will be pegged to the US dollar. The system is meant to be such that someone could fork this code base, swap out WETH and WBTC for any basket of assets they like, and the code would work the same. Now, we understand what this code base is, but some of you may be installing Moccasin for the first time, so I do want to just talk through this with you. We do go through this on the Updraft courses, but we can simply run through it here as well. So we've got the Moccasin installation documentation on the cyphering.github.io/Moccasin. So if you come over to here, if you already have UV installed, all you need to do is head over to Codehawks. You can see that we've linked the repo here. You can go into your VS Code. We want to copy the link here. We're heading over to VS Code. We're opening a new terminal. We are going to do git clone and paste in the link here. We should already have, I'm not going to do this because I've already cloned the repo and we've already got it set up. But following the installation documentation here, to install Moccasin, you just need to do UV add Moccasin. We clone the repo. We change directory to be in the repo on our VS Code. And then we can start building. So we are going to run mox install to install all of the dependencies for our repo. And then we can run mox test. And those tests are all going to run successfully. If there are any issues when it comes to the installation or the building of the repo, then please head over to our Discord. The link will be in today's description. In there, you can ask some questions and we will help to try and debug this all for you. But it should run very simply. That's all that you have to do. Mox install, mox test once Moccasin is all installed, and it should work all well. So now we've got that all set out. You can see that when we run mox test, it is very similar to Foundry, where you do forge build, forge install, forge test, but it's mox install, mox test instead. It will have a lot of similarities because that is the way that it is being built. Let's take a look, though, through the different contracts, the different Viper contracts that we have here to understand the code base for this week and prepare for this first flight challenge. Now, I have made a small description of the code base here just so we can understand the intended functionality before we run into those contracts and look at the different functions. So the intended functionality here is for a user to be able to deposit some collateral and receive some stable coins in return. This is an algorithmic stablecoin. So we've got an example here. So we have a user. They call the deposit collateral function, and they send $200 worth of ETH to the contract. They can then mint some of the stablecoin, which is DSC, using the mint DSC function, and they will receive 100 DSC in return. Now, the user can mint up to a safe limit, and that is determined by the health factor. This is similar to other algorithmic stablecoins as well. To touch on this health factor further, we're looking at the ratio between the amount of the collateral that has been deposited versus the amount of stablecoin that has been minted. This should actually be wrapped ETH, as we saw in the description. This protocol is meant to be for wrapped ETH and wrapped BTC, but that is all determined upon deployment. So let's imagine that we forked it and decided ETH is available for this. So taking a look at that health factor to understand a little bit better how much a user can mint depending on how much they have deposited. We're looking at the debt over the adjusted collateral value. So initially when we set up, we're looking at the initial collateral value. So if we have a health factor of 1.2 and a user deposits $200, they have the ability to mint up to $80. So that this is a liquidation factor, but we'll come back to this in just a second. So they have the ability to mint more than $80. So this would be in reverse. So they will mint up to a specific amount of tokens that they are able to do so. And then there's two scenarios that play out here. The first scenario is the user decides they want to burn their stablecoin tokens, their DSC, and they want to receive their collateral back. The second scenario is their collateral is no longer worth what they thought it was, and we need a liquidator to come and save the day. So let's look through the first scenario here. What we've got is a user has borrowed $100 worth of DSC, and they're ready for their collateral back. They send the DSC back to they burn the DSC actually, and they can redeem their collateral using the redeem collateral function and receive their $200 worth of ETH in return. We can actually combine these two operations into one using the deposit collateral and mint DSC function. We'll run through these functions in the contracts as well within VS Code. But this does all of it for us, and it burns the $100 worth of DSC and mints the $200 worth of ETH all in one function call, which is nice. The second scenario is the more interesting scenario. So in our case, what the user has done is they've deposited $200 worth of ETH and they've minted $100 worth of DSC. Now, If the value of ETH drops to a certain point, which means the health factor falls below 1, what is going to happen is a liquidator is going to jump in, and a liquidator is going to deposit 100 DSC, and in return, they're going to receive $110 worth of ETH, because 10% is what we've deemed to be the bonus in this protocol. So the liquidator walks away with an extra 10% on their funds. It will be in the collateral token rather than in DSC though, and the user who is under collateralized will have lost their collateral and keep the tokens that they have got. So the liquidator is in a bonus and the user has unfortunately been liquidated. So I hope that diagram shows and explains this in a little bit of detail before we run into the code base. The code base should make a little bit more sense now. So let's run through the different functions that we've got here, starting with the decentralized stablecoin. We're going to run through this slowly because a lot of you may be looking at Viper contracts for the first time this week since the courses have come out. So we will just talk through this all quickly. First of all, similarly to how Solidity contracts are written, you're going to have the MIT license at the top, or any other license that you choose to use. We're going to have the version as well, just like we have the Solidity Pragma statement at the top. This is the alternative there. We are going to title the contract, and we are going to give some more information for the developers. Now, the first step to really get started is to import the relevant contracts. So here we are importing different contracts. We've got some contract module that restricts access to certain functions to the owner of the contract. So this is just like the Open Zeppelin ownable contract that we use in many of our different projects and many of our different first flights. This is the Viper alternative. And we have a custom interface for additional functionality specific to the stablecoin in our interfaces folder. So this is just importing a contract that we've built in our interfaces file within our source folder. And this is just importing it there so we can use the different functionality. So again, very similar and very comparable to how Solidity contracts are written. And you'll see that that's a running theme throughout these different contracts here. We are then implementing these contracts. We are initiating the ownable module for ownership management so that we have an owner of this contract, just like you see with typical Solidity contracts. I think I'm going to be saying that a lot here. And we are going to initialize the ERC20 functionality as well. And we are making the owner of the contract the controller of the minting and the burning functions for this ERC20. We are then going to name it, give it a symbol, the decimals, all of the standard ERC20 metadata is going to be in this section of the contract. And now we move on to the constructor. So the constructor, you can tell it's the constructor because we have this init title. This is how we label a constructor within Viper contracts. As you can see here, we are taking in the name, the symbol, the decimals, the name, the EIP 712 version as well in that constructor. And then we are defining which functions and properties are publicly accessible. So you can see all of these functions here, of which are imported from the ERC20 contracts and the ownership contracts that we imported earlier. So I hope this all makes sense so far. That is the decentralized stablecoin contract. Essentially what we're doing is we're importing ERC20 standard and we're importing the ownable contract, and we're just initializing it all in there so that we have this token that we can use as a stablecoin when we are minting and burning in the next contract. So this is just initializing that. We essentially here have created the DSC token that will be used within the stablecoin algorithm. So let's take a look at that. And this contract is called the DSC engine. So this is the contract that we are interacting with to burn, to mint, to deposit collateral, and everything else we have just discussed throughout that diagram. Taking a look at this contract to start off with, we are looking the exact same as the previous. We've got the version, we've got the license, we are using MIT in this case. We've done the title, author, and some information for the developers as well. So this is an anchored token pegged to US dollar. It's decentralized. And we are looking at depositing collateral to receive some of these tokens. So running through what's been imported here, we have a couple of contracts that have been imported. Again, we are importing a contract that we have written in our source folder, our Oracle. We will look at this contract next. But as you can imagine, it's just an Oracle. We're getting price feed data. We're getting the value of different tokens so that we can properly determine the health value for the collateral and the liquidation of users throughout this contract. Other contracts that we are importing, we have the interfaces that we have built here as well, and we have interface IERC20 there. So everything that's is imported and ready to go. Now we need to initiate some state variables here. So we have the liquidation threshold, we have the liquidation bonus, and so we're looking at the minimum collateral ratio for this protocol. We're looking at the bonus collateral received by liquidators. Here it is deemed to be 10%. And this is what we were discussing just a minute ago. If we head into scenario 2 and a liquidator comes to liquidate a user, they receive that 10% bonus there. And that is what is determined through this variable here. The liquidation bonus. We also have the liquidation precision, the minimum health factor. So this is the minimum required health factor to this number determines how much of the stablecoin the user can mint during that initial phase when they are depositing collateral and minting tokens. This also determines the value at which a user can be liquidated. We also have the precision, so the base precision factor. We have the additional feed precision. So here we are adjusting the Oracle price feeds for accuracy. And so we can determine how regularly we would like to receive Oracle price feeds. And we have the feed precision as well. So native price feed precision, so 10.8. So that's the constants variables being initialized here and declared. We also have some immutable variables as well. So we're looking at the DSC contract address. This is the address of the contract we have just ran through, that contract that just initiates this ownable ERC20 token. This is taking that contract address and pulling it into here so that we can interact with that. We are also looking at a list of collaterable token addresses supported by the system, as discussed in the About section of this code base. Let's pull this back up again. So in this section here, you can see that it's intended for wrapped ETH and wrapped BTC to be the collateral tokens in the initial scenario, but it's intended that the system can be forked and a new owner can swap out these tokens for any basket of assets that they would like. So opening back up this contract here, that's the immutable variables declared. Let's move in to the storage variables. We're looking at the mappings of the contract here. We have the token address to price feed mapping, and this maps collateral token addresses to their price feed addresses. We have the second mapping, which is user to token address to amount deposited, and this tracks how much collateral each user has deposited for each token. And we have the user to DSC minted, so this tracks the amount of stablecoin minted by each user. So they're the three mappings that we have here. As you can see, as we run through all of these different contracts, we have the initial statements that we see within a Solidity contract. We then import different contracts. We then look at the different variables. We look at the different mappings. We have the constructor, and then we move into the functions. There will be a lot of similarities here. And as I said at the start of the stream, I wouldn't shy away from looking at Viper contracts and auditing Viper contracts and entering into competitions with Viper contracts, because the actual structure is the same and the vulnerabilities are most of the time in the structure of the code rather than the language the code is written in. So you can see the same vulnerabilities, and learning these different frameworks and the different languages will just better and increase your skill set. But let's take a look at the different events that are going to be emitted throughout this contract. We've got the collateral deposited. So this looks at the user's address and sees how much collateral they have deposited. So this is emitted when a user deposits collateral. And then we have the collateral redeemed as well. So we're looking at the token, we're looking at the amount of collateral and the address it's coming from and the address it's going to. Now let's move on to some of these functions. Now within this contract is structured in a way that we are looking at the external functions first, and we will then move on to the internal functions. So you may see throughout this section of the contract that it's relying on other internal functions that we will discuss later. So first of all, we have the constructor for this contract. You can tell this because it is defined, the function name is the init, and we can see here that this is just initializing those price feed addresses, the token addresses, the DSC token address as well. So initializing all of those contracts so it can all work together as it should. Now moving on to the external contracts, we have the deposit collateral function. This is the function used to deposit collateral tokens. This is the function that will be called to deposit wrapped ETH or wrapped BTC so that you have the ability to mint some of the stablecoin DSC. So this moves on nicely to the next function that allows you to deposit collateral and mint DSC in the same function. This is what we discussed in the diagram. If we pull this back up, we have the option to either so here we go. We have the option to either deposit collateral and mint DSC in separate transactions, or both combined in this new function here, in this deposit collateral and mint DSC. So we either deposit collateral and then we mint DSC, or we do them both in one through this function here. We also have another function that redeems collateral for DSC. So this is when we are coming back and we are saying we're ready to burn our stablecoin tokens and receive our collateral back. So we can redeem collateral for DSC throughout this function, or we can do this separately through redeem collateral. First we burn the DSC and then we redeem the collateral. These two functions are combined in this redeem collateral for DSC function. So I hope this all makes sense so far. I know we're running through this quickly, but you'll be able to see as you go through the different functionality and that we have this breakdown of functions. It's pretty simple what we're going through here once you understand that diagram that we went through earlier in today's stream. The next function here is the liquidate function. So going back to that diagram, there's two scenarios. The first scenario being that a user decides they want their collateral back, and the second scenario being that the user's collateral drops below a healthy value and a liquidator comes in to earn some of the bonus. So going back through this example very quickly, if a user comes to the contract and deposits $200 worth of ETH and then mints $100 worth of DSC, if the value of their ETH drops below a healthy value, for example, drops below $100, the loan is then under collateralized. How a liquidator can benefit from this is they can come back, deposit the 100 DSC into the contract. So this mitigates this issue. And in return, the liquidator will receive $110 worth of ETH, which is the collateral that the user deposited. So the health factor isn't usually one in a real scenario. It will be slightly different so that we can get that 10% fee for the liquidator to incentivize people to be liquidators. So this is the function that we are using to do this. So this is the liquidate function. A liquidator will come in and they will liquidate and they will receive that 10% bonus that we defined earlier. Now, when we are forking this protocol, when we are deploying this protocol, we can actually change around with that bonus fee to be more desirable for liquidators or to be more beneficial for those who are depositing collateral into the contracts and reducing that health factor slightly. So that is the different functions that we're looking at in the DSC engine. Now, these are all the external functions. So you can see these are all the ones that we'd be interacting with. But if we take a look at these functions, you'll see within them, we're calling a lot of internal functions as well. So let's skip down to the internal functions quickly. We've got the deposit collateral function. We have the mint DSC function. We have the redeem collateral function, the burn DSC function, and the revert if health factor is broken functions. These are all functions that will be used throughout those external functions, just further down. So we don't need to cover those too much within this stream, but just understand that when we're calling different functions through these external functions, we need to review what's further down to understand how they are fully operating. Moving on now to the pure and view external functions. This is just so a user, as with any view function, can look at the data and retrieve data and understand what the health factor is, what the amount of tokens they've deposited is, what the collateral is looking at, how much they've minted if DSC, all of these kind of things, the value of their collateral in US dollars. All of these kinds of things can be seen and retrieved through the pure and view external functions within this contract. We don't need to run through them all. They are pretty self-explanatory. The function titles do a good job of explaining what they are. Moving down there, we've been through the internal functions. We've got the pure and view and internal functions as well, all involved within the internal functions. These are all called within the contract to provide information and execute the different transactions that are happening there. So that is the DSC engine. This is basically the core functionality. The contracts around that are just there to support this function, and this is the main one. So the two contracts that are here to support it are the ERC20 creation contract, which is the decentralized stablecoin.vy file, and then we have the oracle_lib file as well. So this is the Oracle. This is using Chainlink Oracle, and this is going to retrieve data for the decentralized the DSC engine to run as it should. We need to be looking at the values of the deposited collateral to make sure that people have a good health score. And if they don't, we need the DSC engine to be able to recognize that so that liquidators can come in and liquidate those users with a bad health score. So all this data is retrieved from the Oracle Library Viper contract. It's just got two functions in here. We are determining a time period within this contract. This time period is the maximum allowable time in seconds since the last price update. So here we have 3 times 3,600 seconds. How many minutes is that? I don't want to do that in my head. But after this is the maximum amount of time between each Oracle call. This means that the value of the collateral is not going to be out of date, or this is the maximum amount of time between each oracle, so that we don't determine how much wrapped ETH is one day and then not check it again for another 2 days, because we all know the volatility of these markets. So this makes sure that every couple of minutes we determine the price of the wrapped ETH, the wrapped Bitcoin, the collateral that's been deposited into the contracts, and make sure that we have this constant stream and constant up-to-date data. Otherwise, people could take out huge loans and we could have huge price fluctuations, and the collateral they've deposited could turn to zero before we are notified of it. So this is why we need a constant stream of data. So we have the different functions here. We have the stale check latest round data function. This checks the latest price data from a Chainlink price feed and verifies its freshness. And we have the stale check latest round data. So this is going to check for 2 different things. First of all, that the data has been updated recently and that the data is not invalid or incomplete. So these are the 2 checks that have been done there. And all of this information is fed into the DSC engine to support that and make sure that people's collateral and health scores are where they should be. So they're the 3 functions that are in scope for this code base. We've ran through the different users here. We have the user who's looking for depositing collateral and receiving the stablecoin, and we have the liquidator as well. You can see this information within the CodeHawks platform too. So if you go to not the getting started section, the scope section, the known issues section. Well, we've been through the users, the actors of the code base in today's stream. I will share actually a screen grab of this diagram so you can review this within the Discord if you think that would help. So head over to our Discord. The link is in today's description. I will drop the screen grab of this so you can review this and quickly see how these contracts and this protocol is intended to function, and that will help give you a head start to determine where there are some vulnerabilities hidden within this. All of the information, as I said, is within the getting started and the contest page on CodeHawks. But if you do have any questions, you can pop them in the Discord channel and we will answer them as quickly as possible. It looks like we don't have any questions within the live stream chat today, which is a good sign. Hopefully that means it's all being described clearly. But if you do watch this later on, or if you do have some questions later on, head over to that Discord and we will be in there. But I think that is a pretty thorough run through of the code base today. 30 minutes is much longer than our typical first flight streams, but since this is well, we've had Viper contracts on the CodeHawks platform before, but since this is the first one in a while and the first one using Moccasin, I thought we'd go into a little bit more detail. But I hope that helps. If you have any questions, as I said, let us know. But that's all for today. So thank you very much for watching, and we will be back in 2 weeks with another first flight. So make sure to subscribe, like the video, and head over to the Discord to get involved and see what questions other auditors are asking, because that's always helpful and may direct you in a specific direction. But that's all for today. Thank you very much for watching, and goodbye.